Okay, welcome back everyone. We're going to wrap up our discussion of 2D kinematics by considering relative motion. So we're trying to figure out what is relative motion and relative velocity, and how do we calculate it for moving objects. Okay, so relative motion essentially is the idea that observers moving at constant velocity relative to each other will think of each other moving at different speeds. So these moving observers will agree about some aspects of their motion, but not about everything. And let's take a look at a concrete example to see this. So let's say we have two observers, A and B, in a particle. And let's say that B is moving relative to observer A. So if I'm standing at rest as observer A and you're running away from me, then I could report that you have a relative velocity. We could say that this is the velocity of B with respect to A. So that's what that comma means. And then let's also say that there's a particle that's moving with respect to the observer. Okay, and let's say that this is velocity B with respect to A is equal to 10 again. Okay, and let's just say, for the sake of argument, that it looks like, from A's perspective, it looks like P is moving to the right at twice the speed that B is. So we would actually want to write this as the velocity of P with respect to A, and that's equal to 20. However, if we switch our perspective to observer B, it looks like P is moving to the right at the same speed that A is moving in the opposite direction. And this speed is half of what A thinks P is doing. Okay, so in other words, the velocity of A with respect to B would be negative 10, and also the velocity of P with respect to A would be positive 10. Okay, so how does this come about? Well, when you multiply matrices in math, sometimes what you do is you line up the indices. So let's say that A was m by n, and B was n by q, just to make up some random numbers. If you want to multiply them together, then you have to multiply A times B in this order to give you matrix C, which would be m by q. It's like that middle guy drops out. Now, one way to think about relative motion is that if you align the subscripts the same way, then it works out. So for example, you could write this any number of ways, but one way to do this is to say that the velocity of particle P with respect to B is equal to the velocity of P with respect to A plus the velocity of A with respect to B. Okay? Now, it turns out that this velocity, which is measured by two observers, depends on their velocity relative to each other. So this is kind of another expression of what I just said. Okay, that the relative velocity depends on the two individual velocities. Could also write it like this, that VA is equal to VB plus V relative. So I've just brought it to the other side. So as an example, we're going to show that even though the velocity of these observers is different, the acceleration that they measure for a third particle is the same, provided that V relative is constant. And actually, this is pretty easy to do. We're just going to take the derivative of this with respect to time. So the derivative of VB dt is equal to the derivative, if I can write, of VA with respect to t minus the derivative of V relative with respect to t but we're told that v relative is constant, so that means that this derivative drops out, and we simply have that these guys are equal. So therefore, the acceleration that b measures is the same as the acceleration that a measures. And this is important because when we talk about forces next unit, we'll be talking about the idea of transformation of velocities. Okay, so observers will agree on the acceleration but not its velocity. And we'll also be talking about inertial reference frames. So essentially, what an inertial reference frame means is that they can move relative to each other at a constant speed, but observers will find the same value for the acceleration of a third particle, which can be measured with respect to either frame of reference. And it might be impossible to tell which reference frame is at rest, depending on the situation. Finally, Newton's laws, which we'll get to next unit, are true only in inertial reference frames, but not in accelerating reference frames. So we're going to do a couple of quick examples. First of all, how long does it take an automobile traveling in the left lane at 60 kilometers per hour to pull alongside a car traveling in the right lane at 40 kilometers per hour if their front bumpers are 100 meters apart? So that means that v relative between them, if you just think about this, is 20 kilometers per hour. And we're trying to make up a distance of 0.1 kilometers. And so time is just going to be distance over relative velocity. So 0.1 kilometers over 20 kilometers per hour is just going to give us 0.005 hours. And if you want to multiply that by 3,600 seconds in an hour, okay, that's going to give me basically 18,000, but I have to move the decimal place 3 times. So we're talking about 18 seconds. And hopefully that makes sense. Okay, and now my PowerPoint doesn't want to work. So I'm going to sort this out and then I'll be right back. Okay, we're back. Sometimes the PowerPoint just has a little bit of a hiccup on this tablet. And so we're going to do one more example problem. Okay, so the pilot of an airplane notes that the compass indicates a heading due west. And the speed of the plane relative to the air is measured to be 150 kilometers per hour. And this is like a top view. And we're also told there's a wind, which is basically the speed of the air with respect to the ground, of 30 kilometers per hour to the north. So we want to find the velocity of the plane relative to the ground. So we're looking at finding this hypotenuse here, because if you think about it, the velocity of the plane relative to the ground is the vector sum of the velocity of the plane relative to the air plus the velocity of the air relative to the ground. And so you can see that this is kind of what I was talking about, where those middle terms sort of cancel out to give you what you want. So it's just Pythagorean theorem, and we're going to get about 153 kilometers per hour. And this angle right here is about 11.3 degrees north of west. Okay, so that wraps up things for projectiles in two-dimensional motion. Next time we're going to start talking about forces and getting into Newton's laws of motion.